Okay, let's, I guess, get started. First question is there any discussion about, any questions about projects or anything like that? To get started. Okay, so what I wanted to do today is, today I'd like us to start the transition into kind of more the machine learning part of the course. And the to do that, I think it's important to review some linear algebra. I know everybody here has had linear algebra, at some point, probably a fairly long time ago. But I just wanted to kind of discuss, linear algebra is kind of the mathematics of matrices. And we're going to be working in here on, you know, you know, the data sets that we look at are usually can be thought of as matrices. And so, again, in a data matrix, we typically have rows that are the examples and columns that are features, okay, or attributes. And when you have a data project, usually all the stuff we've talked about so far has largely been how do you build your data matrix so the features mean something. Um, but now let's talk a little bit about the matrix. And like I say, linear algebra is kind of the language of matrices. Many of the machine learning algorithms that we're going to talk about here are either defined or thought of through linear algebra. And my goal is not to review your linear algebra course. I will attest that I hated linear algebra when I was a student, and you'll see why in a minute. But there's some things that are useful to know, and that's what I'm going to try to talk about today. Professor, the camera isn't showing the full global view. Okay, let's see if we know how to change this. That's a good question. Hold on, sorry about this. Okay. Give me 1 minute. I don't know if anyone knows how to change this. We've had this problem once before. Let me just try to deal with it. Hold on. No. Device control. No. No. Uh-oh, now it's worse, right? Camera. Okay, hold on. Presets. Wait. Okay, hold on. Is this better? No. Wait, is this better? No. Okay, hopeless. I've probably now ruined it, right? No. I think I'm on the laptop webcam is true. Oh, actually, wait a second. I've ruined it, I think. But let me go back to. Okay, hold on. Sorry about this. Okay, sorry. I think I have just messed this up badly. Okay. Sorry about this. Okay. Now, let me say, stop video. That doesn't change what you guys can see, right? Okay, guys, I am in trouble, and I'm gonna have to abandon this for a minute. Okay. I think this is gonna be a problem. Okay. Sorry about this. Hi there, I think I've got my AV problem, self-inflicted, but can you come down? 120, thanks. Okay, sorry about that, guys. Okay, okay. Okay, the good thing is it's now working for here. The bad thing is that we agree the camera isn't the position we would like it to be. But I think somebody's going to come in a minute to help me out. So let me keep started till he comes. And again, if you need the slides and you can't see this now, remember my slides are on my webpage. This is lecture 15. Okay. So what are matrices, and why do we care about matrices? Well, matrices can represent many different things. You know, we are used to thinking in terms of data matrices. Data matrices, again, we have a row for every item. Okay, hi, these people are noticing that I'm on my webcam. I think I am plugged into this thing.
Yep.
They want the room. Yes.
No, we want.
They want something like this.
No, we want this. Let's see.
Okay, you figure it out. I don't know what happened.
Better?
Good. Okay, that's better in TV land? Okay, thank you. Sorry about that.
Not a problem.
Okay, thank you very much. Okay, so again, what do we want matrices to represent? The classic example was the data matrix, where you had rows corresponded to items or samples. The dimensions, the columns represented features. We can also think of a matrix as a collection of geometric points. Each row represents a point in space. Each column represents one of the dimensions. Okay, and sometimes that's the useful way to think about it. We can think about matrices as systems of equations. In a system of equations, what do you have? You have a equation in d variables, a linear equation. You have some equation like this. You've got 3 dimensions. The coefficients represent the contents of the matrix. This would be 1. This would be 3. Okay? You could represent an equation by storing once the order of the variables is fixed, You can represent it by just the coefficients, and thus we could view a matrix as being a system of linear equations. Another way to think about matrices is we can think of them as representations of graphs or networks. If we have an n by n matrix, okay, an adjacency matrix is a case where value ij denotes whether or not there is an edge from I to j, or how many edges there are from I to j. Typically, in an adjacency matrix, it would be 0 or 1, okay? We could also have that represent the weight, so that you have a shortest path problem. Maybe ij represents the length of an edge, okay? And sometimes it's very useful to think about graphs as matrices. Vectors are sort of d by 1 matrices, one-dimensional matrices. And often we will think about just any row or any column as defining a matrix. Any questions? So matrices are useful because they can represent lots of things. Now, linear algebra is useful because you can come up with very, very concise formulas that represent things that are often the products and sums of matrices and other matrix operations that can express very complicated things. Does anyone know what this is? You see in a matrix formula here. I don't know if that looks familiar to anyone. What is this? Okay, has anybody ever seen this thing before? Okay. This is the algorithm for linear regression. That's right, coefficients from regression. Okay, and you can represent, the linear least squared curve fitting, which many of you have used presumably on the homeworks. How did you compute it? Well, you took your matrix of points. That's typically what we had there. We had data, data fields. We may have thought them as points in geometric space. You took the matrix, multiplied it by its transpose, took the inverse of it, multiplied it by the transpose, and then multiplied it by the target values, okay? That there was you had a bunch of x's determining y. You were trying to build something to predict y. W was the vector of coefficients, okay, that best predicted the results. Now, there are two reactions when you see an equation like this. One is to be amazed that something as complicated as an algorithm for linear regression can be expressed like that. The other reaction is, my God, where did this come from? And this is the reaction I often have, because I have a hard time, I grew up sort of doing combinatorial algorithm design and stuff like that. Jimmy Joseph, okay, someone is sentencing you to turn off your microphone, if that's on, and hopefully that solves the problem. Anyway, I have a hard time interpreting linear algebra results. And one reason goes back to proofs like this. If you look at something like this, how many of you have ever seen a proof that 2 equals 1? Okay, many of you. Now, what does it mean? In some sense, it means nothing, okay? But it's a very convincing looking proof that you start with, and if you go from one line to the other, okay, it all proceeds by sort of algebraic transforms before getting to a surprising result. Where is the deficiency in this proof? I don't know if anybody here believes it's true. Divided by 0, there is this line here where if A is equal to B, A minus B is 0. Okay, and when you do it, when you're doing this cancellation, we're used to canceling things in algebra. Really what canceling is dividing it by, multiplying it by 1 over the thing that you're canceling on, because you can multiply both sides of the equation by the same thing. So what is the lesson from that, at least to me? First of all, I was never very good at algebraic proofs, okay? They never really kind of showed me why things worked, okay? I could kind of believe, I could go through and follow the steps, but I could very, very easy, they're very easy to verify in some sense, because you just go step by step. But you have to watch for kind of special cases. Again, things like dividing by 0. In linear algebra, when you work through the theory of linear algebra, everything is clean and beautiful, but you do get things that are, kind of singularities, things like matrices that can't be inverted. And, obviously the results don't hold for things like that. So I'm not going to spend today going through reviewing all of the, kind of proofs that you did in your linear algebra class. I do want to point out some concepts that you covered in linear algebra that I think are valuable things to know about when it comes to data science. So one thing that you learned was this idea that you could represent points in D dimensions by unit vectors and their magnitudes. What did that mean? Okay, if you have points in space, you have some kind of an origin. Any point and the origin defines kind of a direction, defines a vector. Okay, and that vector has a length, the distance from the origin to the other point. And if you divide your vector by that length, you get a vector of length 1 that points towards the target point. That director of length 1 we call a unit vector. And, one thing, a kind of normalizing data points, can be sort of thought about like reducing everything to a unit vector. Sometimes that's a useful form of normalization. And one reason it's useful is because it makes, it turns distance comparisons into angles. So if you want to say something about how far apart 2 points are on the unit sphere, okay, one thing to think about is to reduce those points to unit vectors and find the angle between them. If the angle between them is small, then the points are very, very close to each other on the sphere. If the angle between them is large, they are far apart. And this is something we can do because there is a relationship between, for any 2 vectors, okay, the dot product of the 2 vectors. What's the dot product? We'll talk about it, I guess, later on. But if I have a vector x1, x2, x3, and y1, y2, y3, the dot product was x1 times y1 plus x2 times y2 plus x3 times y3. Okay? The dot product of 2 vectors divided by their magnitude, the magnitude was just basically the distance between 2 points, okay, gave you the cosine of the angle between them. And so one thing that's often a useful thing for us to do is to compare, if we want to measure the similarity of 2 data sets, two rows in a matrix, okay, is to compute the angle between them. And what's interesting about it, what is the range of values that the cosine can take on? Okay, you remember cosine? -1 to 1. And what else have we done in here that is minus 1 to 1? Correlation coefficients. And so one way to think about it is that the scores of cosine similarity, they're not like distances, okay, in a geometric sense, but they are like correlations. And basically, if we had normalized the vectors to unit vectors, basically the dot product, okay, the cosine is going to be the correlation between them, okay? And again, if we think about what happens, the cosine, if you have two angles that are same, again, I have just to remind myself of this. The cosine, remember, of an angle theta was the x part, right? And so if you have two unit vectors that are on top of each other, okay, the cosine was going to be 1, okay? If you had two angles and the angles were, kind of right angles, the cosine of it was 0, okay? And if you had an angle that was so big it was basically like a line, the cosine was minus 1. So this kind of gets basically the idea that when the cosine is positive, it's like a correlation that's high. When the cosine is 0, it's like the vectors have nothing to do with each other. Okay, in fact, like they're orthogonal to each other. Okay, any questions about that? So this is why people often talk about cosine similarity. Any questions? Now, in I'm going to talk about some other matrix operations today, and I use these pictures to try to help us visualize them. So think about an image. Again, I didn't have it on the slide, but an image can be thought of as a matrix of pixels. And so here I've got two matrices associated with our 16th President Abraham Lincoln. We have his face, we have his memorial in Washington. Okay? So what operations on matrices are important? In the formula, we had this matrix operation called a transpose. A transpose is the interchange of rows and columns. So if I have an A by B matrix, the transpose is going to be a B by A matrix. Okay? And the transpose, it just basically is a rearrangement operation. Okay? Any questions about the transpose? If we have matrices of the same dimension, okay, if they're both A by B and A by B, we can add them up in a pairwise manner. The element of the sum is going to be the sum of the element, ijth element of the sum is the ijth element of the first one plus the ijth element of the second one. So we can add matrices. We can also multiply matrices by scalars. You can imagine a world where you take a constant like 2 times a matrix, and that's going to multiply every element in the matrix by 2. If we do that, we can now talk about linear combinations of matrices. This is if you kind of view each one of these images, you can kind of think about trying to morph from one image to another by basically coming up with a matrix that is a linear combination of it. Okay, if alpha here is equal to 1, then 1 times A, that's going to give us matrix A. If alpha here is going to be 0, it's going to give us matrix B and slowly fade between them. Any questions? Okay, but the main operation that happens on matrices that is important for us was the dot product. Again, we showed what was the dot product? Well, if we have an X by Y matrix and a Y by Z matrix, okay, the inner dimensions of these matrices is Y. That means that each row here is a dimension that's the same size as each column of the second matrix. The dot product of two matrices, as I said, is simply going to be, we're going to sum up over the k pairs and multiply the corresponding element. So the dot product of the first row and the first column was 7 times 1 plus 2 times 8, 9 plus 3 times 33. Okay? And as we saw, the dot product, to find the cosine of the angle, okay, the dot product measures how in sync the matrices are. If the matrices are in sync when this one is big, the corresponding one in the other vector is big. Okay? So big things we would expect, big dot products correspond to highly correlated things. Small dot products correspond to things that are not really in sync. When one of them is large, the other one is small. Any questions? Okay. Now, and again, matrix multiplication basically reduced to, if you have an X times Y matrix times a Y by Z matrix, you basically came out with an X by Z matrix, each element of which was a dot product on vectors of size Y, dimension Y, and therefore the time it took was X times Z times Y. Okay? You've seen the simple loop program to compute the products of matrices is something that takes the product of its dimensions. There are faster algorithms for multiplying matrices, and more to the point, faster libraries for multiplying matrices. So a lot of what goes on these days in you guys know that neural networks, okay, are of course a popular thing. Neural networks, the basic loop on the inside is often computing the dot product at every element between the weights of the node and the value that's kind of coming into it. That's kind of the elementary thing. So evaluating neural networks reduced to computing matrix multiplications. So the world has gotten very good at doing matrix multiplications. This is what people do with GPUs when they're training networks or evaluating them. And people have gotten good at building libraries for sparse matrix multiplication. So as we'll talk about later on, there's certain operations in matrices that basically rearrange things. Often these days, it's easier to rearrange things or faster to rearrange things, the elements of a matrix, by multiplying it by another matrix, rather than doing the logic for rearranging it, okay, as hard-coded things. And that's sometimes useful. What other properties of matrix multiplication are interesting? It is an associative thing, meaning that if you have a long chain of matrices, you can group it however you wish. You could multiply the first two and then times the third, or you could multiply the second two and then times the first, and you'll get the same answer. That means it's associative. But matrix multiplication is not commutative, okay? Matrix A times B will give you doesn't necessarily give you the same answer as when you multiply B times A. So you can, group them as you wish, but you can't rearrange them. And perhaps the most special case where you can rearrange them is when you multiply something by an identity matrix. You have the identity matrix, which is just ones along the diagonal and zeros elsewhere. The identity matrix times A gives the matrix A, as does A times the identity matrix. Any questions? Okay. But let's think what good. So I think everybody remembers what how to multiply matrices. But what is the meaning of multiplying matrices? This is where I think things get to be kind of interesting. Suppose I have a matrix that is an n by d matrix. What happens if so there's n rows, I'm going to call them rows, and d columns in my data matrix. What do I get when I multiply a matrix times its transpose? If we think about A times T, A transpose, okay, the matrix is going to be n by n. Okay, why? Because this is an n by d matrix. The transpose is a d by n matrix. We're going to get an n by n matrix of dot products. Okay, and each dot product is going to be of order d, the number of dimensions. A times A transpose is a matrix that measures, in some sense, the similarity between the rows. For every pair of rows, you're getting a sense of how similar it is, how in sync it is. If we take A transpose times A, what do we get? A transpose is going to be a d by n matrix times A was an n by d matrix. We're going to get a d by d matrix that is going to measure where each row, each element, is going to compare basically over all the points how similar were the two dimensions over the 2 points. So this kind of measures how in sync the features are. Okay, this measures how in sync the points are. These matrices, A times A transpose and A transpose times A, they are common enough things that they give them names. They are called covariance matrices. Any questions? Let's think back to our Lincoln Memorial and take a look at the covariance matrices of it. Again, I get confused. A times A, this is A. Is A times A transpose measuring how in sync each row is? Okay. Remember, this is the number of rows times the number of features. Number of features times the number of rows. This is going to measure how in sync every pair of rows are. Okay? And if you look at the Lincoln Memorial and you look at the covariance matrix, I think it kind of makes sense. What is this blob, this dark square corresponding to in the covariance matrix? Okay? I claim that that is because if you look at this, every one of these rows is very, very similar to the one before it, right? And, you know, it's relatively dark. There's a lot of darkness. If darkness means got a higher number than whiteness here. Because every row is like every other row, that is a, what you call it? That is going to be uniform. And because it was fairly dark in many of these spots, when this thing was big, this thing was big. We got it, it was uniform and fairly dark. Any questions? Actually, I guess if you look at what's the darkest thing, these rows times these rows, that's actually even darker up there. Okay? Any questions about that? Now, as you notice, the covariance matrix is symmetric. Okay? And that's because the ith row is as similar to the jth row as the jth row is to the ith row. So we would expect that the covariance matrix is symmetric and that it measures how in sync they are. Look at the steps here. Are the steps in sync with each other? Okay? I think the step rows also look very similar to each other, right? But what's the point? These are a lot lighter than the other ones. So yes, you see steps that are similar to each other, okay? But they are all similar in the light as opposed to similar in the dark. Any questions? Now this was the other covariance matrix, how in sync the columns were with each other. And this, what do you see here? You see a checkerboard. Why do we get a checkerboard for this? Okay, anyone? Because the columns are here. It should be clear that whenever you have one of these worlds, this is a very light row, very much in sync with that light row. Okay? So whenever you're comparing one of the light columns against one of the light columns, you get the light bands. And whenever you're comparing a dark band against a dark band, you end up getting something heavier. Any questions about that? So the covariance matrices are useful things. They are symmetric, and they capture a lot of the correlation effects between variables. Any questions? Okay, good. Now there are other things that when you multiply matrices by matrices, that you end up getting interpretable things. Okay? What happens when you take an adjacency matrix of a graph? Okay, remember, adjacency matrices were typically 0, 1, okay, matrices, depending upon where you know, you had V1 up to Vn, V1 up to Vn, and element ij was telling you whether there was an edge from ij. What happens when you take the adjacency matrix of a graph and multiply it by itself? So you get A squared. It turns out that what you end up getting is a count at every element of the number of paths of length 2. Why is that? If we consider, let's say, A squared, okay, ijk, what is ik going to mean? If ik is going to have a value, if it's the product, A squared, if it's the square of this matrix, what is, let's just think of it. What is the product of A squared? It's basically, the element ij is going to be the dot of the ith row of the matrix times the jth column. What does that kind of mean? Well, if there is I guess I've got my labels wrong to be consistent with what I said. Okay. If there is the only way to get a value for A squared ij to have a value that's not 0, it's going to be the sum of products which are all going, if it's a 0, 1 matrix to start, the sum is going to be the dot of things that are either 0 times 0, 0 times 1, or 1 times 1. Whenever you get a 1 times 1, what does that mean? That means that there is some vertex k. This is I, this is k, this is j, such that ik is 1 and kj is 1. Basically, that when you square the matrices, you get the number of paths of length 2 between every pair of vertices. Any questions about that? There is also a class of matrix operations where we say that something is a permutation matrix. If I have a matrix where I've got a 1 in every row and column, That is what we call a permutation matrix. Okay? And when you take your matrix M and you multiply it by a permutation matrix, what you end up getting is you rearrange the rows of the matrix. Okay? The rows and columns of the matrix according to this permutation. So sometimes when you have a matrix and you want to rearrange the elements of it, transposing is an example of rearranging the elements of something. Sometimes it's easier to come up with more efficient to come up with a matrix and multiply it by it to do this rearrangement operation. Any questions? What is the most famous permutation matrix to multiply a matrix by? I. If you have a matrix where all the ones are on the main diagonal, then multiplying a matrix by the identity matrix leaves it the same. Okay? And it's just one of that family of things. Any questions? Any questions about permutation matrices or any of these kinds of things? There are other interpretations of matrix multiplication. One is we said that matrices could be interpreted as points in space. Certain geometric operations on points in space, like rotating the space, okay? Turns out if you take your points and you multiply it by the right matrix, you can do multiplication. You can basically rotate your points by any angle, okay? And manipulate your point set in that direction. Any questions? Outside of multiplication, we have addition. We didn't talk about subtraction, but subtraction was just multiplying by a negative constant, -1, a scalar of -1 and adding it. The other elementary operation we're used to from algebra is the idea of division. Now, division of matrices isn't really talked about. You hear about inverting matrices. But the way to think about it, inversion is that inversion is kind of like the division thing. What is the inverse of a matrix? Given a matrix, given a matrix A inverse is the matrix that when you multiply A by its inverse, you get the identity matrix. And that is really kind of like saying that that A divided by the inverse, okay, gives the identity matrix. It's sort of like saying that, again, in normal algebra, A over A is 1. In general, if we have A times A inverse, if we multiply both sides of the matrix by 1 over A, okay, well, 1 over A times A should cancel out. I over A, we end up getting that the inverse is really can be thought of as the identity matrix over A, okay? And so there's a strong link between division, what we think of division as inversion. Any questions? Now, how do we find the inverse of a matrix? When you took linear algebra, this was something you had to do. For small matrices, there was a formula here, okay, which said that the inverse of a matrix, of a 2x2 matrix, was this thing, okay? There were formulas for 3x3 matrices and yada yada, okay? In general, there is a procedure using Gaussian elimination, okay, to find the matrix's inverse. What was Gaussian elimination? We had a world where, suppose we wanted to find an inverse, okay, of what you call it, the inverse of this matrix. The inverse of a matrix, remember, was what you multiply it to get the identity matrix. So what are we going to do? We're going to try to use Gaussian elimination, if we're going to use Gaussian elimination, to reduce this to an identity matrix. But then we're going to perform the same operations on what was initially the identity matrix. Okay? So again, Gaussian elimination reduced the variables by adding zeros to this matrix, by adding linear combinations of other rows to it, so that it got to be created zeros where we wanted, zeros and ones. And of course, along the way, if we do that to what was initially an identity matrix, we eventually get an inverse. So finding the inverse of a matrix is equivalent to solving a linear system of equations. Any questions? Now this matrix, if we look at it, is a nice formula for a 2x2 matrix inversion. Does this work for all matrices? If AD, notice that we get a problem here, the same problem we had in proving 2 minus 1, 2 equals 1. If AD was equal to BC, notice that we would be dividing by 0. What would be an example of such a thing? Okay, what matrix would have that property? What? A unit vector? All ones? Okay, so first of all ones would have that property. Right, that's, I guess, the easiest one to see. All ones would have that property. What about 1, 2? What about 1, 2, 1, 2? Would that have that property? Okay. In general, the probability is that certain matrices are not going to be invertible. And they are going to be the ones where, in some sense, the rows of the matrix are not distinct. Okay? That's kind of what's really going on. Okay? There's a higher order principle here. Any questions about that? So what does the inverse of Lincoln look like? Okay, when I took a look at Lincoln, this was the inverse. Okay, I don't know if you see anything there. I don't really see anything. But what happens when I multiply Lincoln by his inverse? What do I get? If you look at it, I get a main diagonal, okay, of 1. And I get this weird pattern underneath it. What is that weird pattern? Okay, if we multiply Lincoln by his inverse, we get a strong main diagonal, like we would like to get. What is the other stuff? This has to do with the error of floating point numbers, okay? Does everybody see that when you're representing, although in theory, L times L inverse should be exactly a, the 0, 1 identity matrix. In practice, when you do these operations, you end up with numerical error, okay? And again, it's the fact that you've only got a finite size word length. If you're dealing with 64-bit floats or 128-bit floats, whatever it is, you're going to have error. And so when you actually try to do a computation on matrices, one thing to remember is that there is, in fact, this error and things don't work out as precisely as when you're dealing with integers, okay, that we're used to. Any questions? Okay. Now, what other good things are true about the inverse of a matrix? Okay. Well, if we take AX equals B, this is kind of the classic statement of a solution of what you call it of a system of equations. What is A? Again, I want to think of it as being, I've got a certain number of equations, which is the number of rows, times the number of columns. The columns were the coefficients, okay, of those equations, okay? And X was going to be the solution of that. What were the values of X that would give us exactly this target vector B? That was what a system of equations were. Every equation was, when you have a system of equations, it's written by C1x times x1 plus C2x times cx2 ... equals y1. y1 means the first element of the vector B. Okay? What happens when you multiply both sides of the equation AX plus equals B by the inverse of the matrix A? A inverse times A magically transforms into what you call it, the identity matrix. So this is the identity matrix times X is equal to what you call it, A inverse times B. And thus solving what you call it, finding the inverse. We showed how we could find the inverse using Gaussian elimination by solving a system of equations. This really proves that matrix inversion is exactly solving a system of equations. Okay? Note that once you have the inverse of a matrix, if you want to solve a system of equations for a different vector B, a different set of y values, okay, it reduces to just multiplying the inverse times that vector. So if you want to compute a system of equations, solve a system of equations, many times where the coefficients of the equations are different, but are the same, but the answers are different. By taking the inverse and multiplying it by each vector, how much time should this take? The vector is going to this is going to be, if X is kind of n by 1 vector, this vector is going to be n by n. This is going to be n by 1, okay? The time to do this product, once you have the inverse, is going to be n times 1, or n squared. So instead of, if you had an original n by n system you were inverting, that took n cubed time. This is faster. Okay? Any questions? So inversion is very tightly tied to this idea of solving linear systems of equations. Now we saw before, okay, that we could sometimes get matrices, matrices whose inverse was undefined. Okay, the ones that were undefined we saw. If we had a matrix where 2 rows, again, what did we know about systems of equations? We knew that n equations were needed to define n equations were needed to solve for n unknowns. That was something that we knew. But it isn't sufficient to just have n equations if the equations are actually the same thing. Okay, again, have n copies of the same equation. Okay, and so certain systems of equations are underdetermined if we don't have enough rows that are really different. Okay, the rank of a matrix is a measure of how many linearly independent rows you have in that matrix. Okay, so if you're going to be solving a linear system of n equations and n unknowns, the rank of that matrix had better be n, okay, for you to be able to find the inverse and for you to be able to do lots of different things with it. Sometimes, actually, did anybody, when they were doing linear regression, this may not have happened in here, when any of you on any of the homeworks did linear regression, did your linear regressions ever crash if you had two different points that were the same thing? Some linear regression systems are going to crash because they are sort of going to be solved using inversion. If you cannot invert the matrix, you can't solve that kind of thing, okay? And so it's important that when you have a matrix, that the rank of the matrix be n. Now, when I tried to do some experiments on the Lincoln Memorial matrix, okay, I got a little bit of a surprise. Remember what the Lincoln Memorial looked like? I guess actually, hopefully maybe we'll have one later on. When I computed what was the rank of that matrix, I should have had a 512 by 512 image. In fact, the rank of my matrix was only 508. Okay? Remember, in the Lincoln Memorial, remember that they were rows. All the stairs looked very similar to each other. Okay? Quite possibly, two of the rows were exactly the same. Or even if they weren't exactly the same, it might have been that 5 of the rows could have been a linear combination of that, might have added up to the 6th row. Okay? Regardless, okay, we did not end up with a matrix that had enough rank to it. So what would I do if I wanted to continue to use these tools? I might want to work on the compressed matrix, okay? Or sometimes a dirty trick is you add a small amount of random noise. And if you add a small amount of random noise to it, you will break the rank of the matrix that you get is going to be now full rank, okay? But it will be you hopefully didn't add enough to really distort it in an important way. Any questions about that? Okay. Any questions so far about anything we've talked about? Okay, again, I picture this is mostly review of stuff that you knew at some point, okay, just to remind you a little bit. Now, one operation that's very important in data science is the idea of factoring matrices. What was factoring integers? Well, how did we factor? Let's say you had the integer, the integer 14. How did you factor 14? Well, 14 had the property that 14 is 2 times 7. You can sometimes express an integer as the product of other integers. You can sometimes express a matrix, okay, M, as the product of two other matrices. It turns out to be a very, very nice thing if you could factor a matrix, okay, into products where the matrices are of sort of lower dimension. So notice that if I have a matrix at A, it could be possible that A is equal to matrix B times matrix C, where if A is an n by m matrix, it could be B is an n by k matrix, and C is a K by M matrix. Okay? If I have that, then when I multiply my N by K matrix times my K by M matrix, I will get an N by N M matrix. If I could factor my matrix A into two matrices whose product gives me A, and if the inner product is, K, the inner dimension is small relative to N and M, then together A and B compress the matrix. Okay? And this can be very, very useful because if A was a feature matrix and B compresses it, B and C compress it, B kind of gives me a smaller matrix that does a lot of the same thing. So when you read about various matrix dimension reduction things, I guess an example that I like to think about is when I think about what might we do with feature matrices on text. Okay, so let me talk about this example. You can imagine a world where, let's say that we have a bunch of different documents. Okay, let's say that each row was a document. And each column was a word. Is this what I want here? Okay, let's hope I got the dimensions consistent. So what is this going to mean? Suppose each document was, let's say we have a bunch of news articles. You could imagine a world where each news article is a row of this matrix. So we want to represent a collection of news articles. Each article would be a row. One way to represent an article as features is how many times does it have each word in it. So you can imagine that every word of the vocabulary, so the number of dimensions is going to be the vocabulary size. You can now say that the ijth element of here is going to be how many times did word J appear in document I. Okay? And if you've got that, you can now represent documents as rows. Okay? And words are, in some sense, what a word means is kind of a column. Okay? Based on what documents it's in. What's interesting with this? Okay? We might want to be able to ask ourselves, what documents are similar? What documents would be similar in the collection? They would correspond to rows with the property that when a word appears in one document, it probably appears in the other one. The dot product would be high. The cosine similarity would be high. Okay? But let's think about a world. Let's think about a world where we have, what is the vocabulary of English? Vocabulary of English that you work with. How many words do you know? You probably know 50,000 words. Okay, there's probably 20,000 words that are in common use. The vocabulary is very large. But what if we could take this document by word matrix, which is easily built from any collection of documents? What if we could factor it in to a number of documents by K by the vocabulary size? Matrices. What is interesting about that? Now, instead of having a document by entire vocabulary matrix, we have a document by some matrix, by some relatively small value of k. Does everybody see that every document still gets a row? Okay? Comparing these short vectors should tell us a lot about whether the two documents are the same. So if we can factor this word document thing, we get a feature vector for documents. We also get a feature vector about words. This is a, k by the number of words thing. Each word has a column here. We would expect that similar words probably have similar, similar columns associated with them. So you would expect that maybe a color like red would probably have a similar feature representation to what a yellow would mean. Okay? Or all the documents that refer to colors might refer to both of them. Okay? Or you can imagine that football and kick might very well be words that are fairly similar. Because anytime you have a word that a document that refers to football, the corresponding documents probably also said somebody kicked something. Okay? So if you believe that, it should be clear that this idea of factoring matrices is a way of taking a matrix, feature matrix, and compressing it into a lower dimensional representation, okay? And finding good lower dimensional representations of high dimensional data sets is a very useful thing to do. When you guys were doing your assignments, how wide was your data matrix? How many columns were there in the bigger of the two projects? I'm hearing 20. Okay, there may have been a bigger number. Would anyone have a bigger number? 40? Okay, whatever it is, okay? It would be, it can be unwieldy to work with a big matrix. If you can find a way to reduce the dimensionality of that data matrix, everything is good. Now, the trouble is, not every matrix, in fact, very, very few matrices can be exactly factored into the product of low-dimensional matrices. But on the other hand, notice we have an approximation sign. When we talk about matrix factorization, we'd like to try to reduce a big data matrix to a feature matrix on rows and a feature matrix on columns, such that their product is approximately equal to that. And if we can do that, that's a useful thing, and there are techniques for coming up with approximate factorizations of these things. Any questions? Okay. So how do we factor matrices? There's some things that you saw in linear algebra that had to do with matrix factorization. One thing was this thing called LU decomposition. Okay, what was LU? L and U stood for lower and upper. It was the idea that you could always factor a matrix, an n by n matrix n, into a pair of, a pair of matrices such that m was equal to L times U. Okay? And that was one matrix factorization procedure that you did learn about in linear algebra. This was useful because it gave you a way to find the determinant. And the determinant was a way of telling if your matrix was full rank. That was one reason why you cared about determinants back then. Here is an example of what happens when, you took my Lincoln Memorial, and after I had added some noise to make it the proper rank, the LU decomposition, it was a lower matrix, triangular matrix, times an upper triangular matrix. When you look at these things, the two coefficients had different properties. But when you multiplied L times U, you got this. What was this? Does this look a little like the Lincoln Memorial? If you look at it, the rows, clearly you're seeing columns, right? The truth is these are all the rows of the Lincoln Memorial, okay? But they're permuted in a different order, okay? When you have a system of equations, the rows, the order of the rows don't really mean anything. And sometimes in the course of doing linear operations, it will permute the rows. In fact, my LU decomposition code that I ran for this thing also gave me a permutation which I could have used to reorder these rows to get it. But so LU decomposition was a a way of factoring a matrix. But there are other matrix decomposition methods that turn out to be very valuable. Yes. Yes.
M is the product of main diagonal of V1.
Okay. Yes, right. So what this tells me is, when you do the factorization, that is a procedure that gave you L and U, right? Now, L and U, it shows, can be packed together into the same dimensions as the original matrix. One of those matrices, therefore, gets the main diagonal. L and U, one of them had the main diagonal, the other one didn't, okay? And, it turns out that, when you get that thing, if U has the main diagonal, the product of that was the determinant. Okay? Any questions? Now, a concept in in matrices that linear algebra that comes up to be very important for compressing matrices and representing matrices turns out to be eigenvalues and eigenvectors. There is a curious property, okay, that here we have a matrix, okay? If you look at this thing, here we have a matrix, here we have a matrix. Here we've got a vector, here we've got the same vector. Here we've got a different vector. Here we've got a different vector, okay? It turns out that multiplying this matrix M by this vector, let's call it U, okay, or V, let's call it V for now, is the same as multiplying some constant times V, okay? And it's a similar thing here, the matrix. This was a vector V1, V1, lambda 1. This was a matrix times a different vector, okay? Was going to be a different constant, okay? Times the same vector. These pairs of constants and vectors that satisfy this equation for a given matrix are called the eigenvalue and eigenvector pairs. And if you think about it, it's kind of a curious thing, okay? A matrix is a big thing. A vector is a little thing. And yet, multiplying the matrix times this vector really is the same as taking the magic constant and multiplying it by the magic vector. So together, somehow, the eigenvalue and the eigenvector must carry a lot of information about the matrix. That's why eigenvalues and eigenvectors are important things. These are kind of smaller things that carry a lot of information about what the matrix is. Any questions? When you took your linear algebra class, you discovered that any matrix that was an n by n matrix of rank n, okay, had n distinct eigenvalues. How did you find the eigenvalues of a matrix? Well, if you took that matrix A and you subtracted it by a lambda times the times the identity matrix. The determinant of it, remember, the determinant of a matrix was an integer. Okay, it was the result of it was basically the result of some kind of polynomial function formed by it was a result of adding together a lot of terms that were products of different rows. The result of this is that you got the determinant of this matrix gives you an equation. Any root of this equation, okay, was represented an eigenvalue. Okay, so by building this matrix, finding the determinant of it, and factoring that thing, you could find what the eigenvalues were of the matrix. And there are faster algorithms for finding the big ones, but basically this is where the determinant was useful. What were useful things about eigenvalue, eigenvector pairs? Eigenvector, eigenvalue pairs. If you had a full rank n by n matrix, you had n pairs of them. Now, if you looked at the vectors, what did we remember when we took the dot product of vectors? Remember, the dot products corresponded to the cosine of an angle between them. If you had a dot product where the cosine, what is the case where the cosine is 0? That was the case where the vectors were orthogonal from each other. So if you took a look at those two vectors from the previous example, okay, the previous example, the vectors were 1, 2, and 2 minus 1. If we take these things, the dot product is 2 times 1 plus minus 1 times 2. The dot product is 0. The dot product of every pair of eigenvectors is 0. That means that the vectors are kind of all orthogonal to each other. And what does that mean? Well, if you think about it, what vectors do you know about comfortably that are orthogonal to each other? If you think about, let's say, axes of in a space, you can kind of think the vectors that define the axes. If this was in 3 dimensions, this is 1, 0, 0. This one was 0, 1, 0. This one was 0, 0, 1. The dot product of every pair of axes is, every one pair of the axes are 90 degrees apart from each other. They're orthogonal to each other. So one other thing that's important about eigenvectors is that they can play kind of the roles of dimensions in a space. Okay? Any questions about that? And, again, you can find what these things are by solving the right linear system. I showed you how, at least with maybe waving my hand, you could compute what the eigenvector values were. We know that the defining equation for an eigenvalue eigenvector pair was A times V was equal to lambda, the corresponding eigenvalue times V. Once you see this, if I have A and if I know what the eigenvalue is, I can, rearrange these things, okay? I can, add minus lambda this thing to that side. This gives me a case where I've got a matrix, okay? dot the vector is going to be 0. Okay? If I plug in the value of the eigenvalue, I get a matrix times V. I can solve for these equations to determine what the value of the vector is. Okay? So by doing these kind of linear algebra things, you can find the eigenvalue, eigenvector pairs. You can also use this equation to find an approximate solution to what that vector is more quickly. If we have an equation like this, okay, where A times V is equal to lambda times V, if we divide both sides by lambda, we say V is equal to A times VL. You can use this as kind of an update rule. You guess what the vector is. This will give you an approximation. You then plug that thing back into this equation, multiply it by A and divide it by the eigenvalue. The hope is this way you can quickly converge on a vector. Okay. We're out of time now. But basically, next class, I'm going to talk quickly about how you use eigenvectors to come up with better compressed versions of matrices before we go on and talk about linear regression. Okay, any questions? Okay, thanks for your attention, and I will see you next class.